Hey guys, okay. Good afternoon, everyone. This is 3272. Okay. First thing I wanted to mention was, so I posted this video yesterday about the questions on the assignment, and the end of the video had like a kind of error. So I just wanted to make sure you all knew that. So let me just briefly say what's happening there. So what I was doing in that video was an example to try and guess whether or not there's the definition for number 5, whether that is a group action. Okay, so I had like some sigma and some tau, and then I computed sigma tau of f, and I computed sigma tau of f. Okay. And then in the video, I said that those two things were not equal when they were equal. So in the video, they were equal. And that suggests that in that question, we have to show that we have a group action. If it wasn't equal, then we're already done, because if this is not equal to this for some f, some sigma, and some tau, then the properties of a group action are not satisfied. Okay. So, but in this example, they are satisfied. So that kind of, maybe that's a good guess as to, well, we should try and prove it's a group action. So that means that you have to prove this equation for all the polynomials f and all the sigmas and taus in S3. Okay, and maybe a plan to do that. Plan for number 5 might be something like, right, well, I think I had tau sigma, not sigma tau, sorry about that. So first, right, sigma f like that, and call that g of x1, x2, x3. Then write tau g of x. Well, that's just g x tau 1, x tau 2, x tau 3. Okay, and then in this equation, just relabel all the x's by y's, and we'll see why soon. So that tau g of y1, y2, y3 is just g y tau 1, y tau 2, y tau 3. Actually, no, sorry, you don't do that. What you do is you call y1 x tau 1, you call y2 x tau 2, and y3 x tau 3. So that's just F y sigma 1, y sigma 2, y sigma 3. And then you substitute y1 equals x tau 1. Wait, did I do this wrong again? Oh, sorry, is my camera okay? It looks okay right now, but okay. Maybe it needs to be zoomed in more. Okay. Okay, so let me try and unravel what's happening here to try and explain it. Okay, so we make this substitution, we put y1 to be x tau 1, y2 to be x tau 2, y3 to be x tau 3. And so that means that y sigma 1 is really, so using this rule, sigma 1 is really x tau 1. So like basically yi is really x tau I. So y sigma 1 is going to be x tau sigma 1. Y sigma 2 is just going to be another name for x tau sigma 2. And y sigma 3 is going to be just x tau sigma 3. Okay, so that means g of x tau 1, x tau 2, x tau 3 is just f of x tau sigma 1, x tau sigma 2, x tau sigma 3, and that is just the definition of tau sigma of f. I'm sorry. And then this is just another name for tau of g, which, and g is just sigma f. This is tau of sigma f. Okay, so this shows that tau sigma f is just tau sigma f, which means we have a group action. Okay. Anyways, that's just maybe gives you a plan. Right. Okay. So did anyone have any more questions about assignment 1? Oh yeah, also for assignment 1, I changed the time that it's due to 8 p.m. Just FYI.
Still have a question.
Yeah.
With the D5 for number one, do we have to use different generators? For instance, for D4, we use the
Okay,
generators.
just a minute. Okay, can you repeat that? Just sorry, my volume was really low.
Yes, so for number one, we use for D4, we use generators A and B, for example. So for D5, would we use generators, say, would we use back generators A, B, or would we use like A, B squared or something? Or does it matter?
So your question is for D5. Well, we should just put D5. We can just use the same A and B. Subject to A to the fifth is the identity, B squared is the identity, and BA is A to the fourth B. Does that answer your question, or does that make it worse?
Well, okay, so I have that, right? But
Right.
when you're actually doing the commutator, you know how you commute AB? I mean, sorry, yes, put AB, yes, like that.
Like that?
Yes, sir. Could you use like A, B squared or like different, like stuff like that now?
Yeah, so let me tell you about just in general, and then I'll tell you about for this question specifically. So in general, what you should do is you should compute commutators of X and Y for all X and Y in the group. Okay, compute all those things, and then take the subgroup that they generate. That's what you should do. Just for like, if I, I mean, I won't ask you to do this, but like, say I gave you some group, I told you to compute the commutator, you'd have to take the commutator for every single element, every single pair of elements in the group. Okay, but for this question, we know that it's generated by A and B. So it turns out the commutator is going to be generated by the commutator of A and B. Okay, so for this question, just compute commutator of A and B. And then that will be whatever it is. And then you take the subgroup generated by that. That's the commutator subgroup.
Okay, sir. Thank you.
Yeah. Okay. The reason is, I mean, I don't want to spend too much time on it, but the reason is because everything in D5 is just a combination of A and B. This will be like, this will tell you about every commutator.
Yes, sir.
Okay, I don't want to say too much about it, but for this question, you're just safe doing this. So yeah, that's fine. Okay, but thank you for that. That's a good question. Anyone else have any, not quite last minute questions, but it's pretty last minute, but anyone have any questions about assignment 5? Or, sorry, assignment 3? Okay, I guess if you think, if anyone thinks of anything, we can always circle back to it. Okay. Okay, so and the things that we've been talking about, so this assignment was about like group actions, and we also learned that a group can act on itself in two ways. Well, many more than that, but at least 2 ways. Just remember we had G acts on G by conjugation. which means that G, the group element G acts on X just by doing GX G inverse. And then G also acts on itself by translation. We'll say by left translation. G times X is just GX. Okay. This is for all X and G and G and G. And the reason I use X here and a G here is because this thing is something that acts, and then this is the set that is being acted on. Okay. It just so happens that the group acts on itself. Okay. And here, this is the group action, and the definition is just regular multiplication. Okay. And then you also, G can also act on the set of subgroups of G. You can do like G times H is just like GH G inverse. And G can also act on the left cosets of some subgroup. You can also do G times XH, just GXH. Okay, so here X equals G, here X equals subgroups of G. Here X equals G, here X equals the left cosets, G mod H. Okay. And then in this situation, we got something called the class equation, which I'll just remind you of. It just says that the number of elements of G is equal to the number of elements in the center of G plus the number of a sum of a bunch of indexes. Centralizer in G of A. Okay, and what this equation says is that the elements of G can be partitioned into conjugacy classes and collect all the conjugacy classes of size 1, and that is the center of G. And then all the conjugacy classes of size bigger than 1, well, they're all like take 1 from each of those conjugacy classes, and the size of each conjugacy class is this index of the centralizer of that element inside the group. And then we did an example of the class equation for D4. Okay. Okay, so what we want to talk about now is a special type of finite group called a P group. Okay, so we have a definition. And these types of groups are pretty special. Let me define what they are first. So let P be a prime number. So all that means, so just to remind you, P could be 2, 3, 5, 7, 11, etc. Okay. And if G is a finite group with P to the n elements for some n greater than or equal to 1, then G is called a P group. P group. Oh, wow, I was really off there, sorry. Okay, so basically you take a prime number. If your group has, the number of elements of your group is the power of a prime number, then you call G a P group. So we've seen some already, at least for P equals 2. We have D4 is a 2 group. The quaternions, that is a 2 group. What else? We can also look at like Cartesian products, Z mod 2Z, maybe to the 4th, that is a 2 group. Let me tell you what that means. I just mean this is kind of the vectors with entries in Z mod 2Z. Okay. So the vectors with entries in Z mod 2Z. This is a group with 16 elements. Okay. In fact, this is an abelian. So like some P groups might be abelian and some P groups might be non-abelian, and there's a great variety of them. Okay. But all we assume is that the number of elements of our group is some power of a prime, and then P is like whatever prime it is, we call it P group. So this is a 2 group. We also have 5 groups or 3 groups and so on. Okay. Maybe I should modify my definition so that the trivial group is always a P group. Maybe that's better. No, I don't want to, sorry. It's just 1. Okay. Okay, why do we talk about P groups? Well, the reason is, let me tell you, sorry. So we can say, why are P groups important? We have, this is because of the Selov theorems. Which tells you what it gives you is it gives information about the P subgroups of a finite group G and the information that it gives depends only on the factorization of the order of G. Okay. Okay, so that means that we can understand things about finite groups if we understand the Sylow theorems and we understand P groups. Okay, so that is kind of our plan. Okay. Okay, so let me give you a proposition about group actions, but where the group acting is a P group. Okay, so this is a proposition. So let P be a prime. So from now on, if I ever say P, I'm talking about a prime number because sometimes I might forget to tell you. But I hope to always say to be clear, but in case I don't. So finite, okay, let G be a P group acting on a set X. Let's say a finite set X. Then the number of elements of X is congruent to the number of elements of Z modulo P, meaning where, let me just remind you what is Z. Z is all the elements in X such that Gx equals X for all G. Okay, so this tells us if a P group acts on a finite set, then the kind of the number of elements of X kind of tells you about the number of elements of the center of the group action. Okay, and the proof of this okay, well, we use a class equation. For a group action, the classic equation for this group action is this. So here we have the stable, oh, this should be A. Here we have the stabilizer of A, the index of that in the group. We have the sum over like representatives of the different orbits. And then here we have all the trivial orbits gathered up into Z. And this equation just says that X is partitioned into a bunch of different orbits. Okay. So now we just notice that for A, the representatives of the non-trivial orbits each non-trivial orbit has size bigger than 1. Okay. But this is a divisor of the order of G. Oops. The index of GA in G divides the order of G, and G is a P group, so the order of G is P to the N. Okay. So a number bigger than 1 divides P to the N. So that just means that this number has to be either P squared, or P cubed, or something like that. Equals P or P squared maybe, or anything up to P to the N. In particular, it is a multiple of P. All these numbers are a multiple of P. Okay, so all of these terms are a multiple of P. When I reduce mod P, they all go away. So therefore, X and the number of elements of X and the number of elements of Z are congruent mod P, as we wanted to show. Okay, and now right away we get a nice result about P groups from this proposition. We call this a corollary. Let G be a P group, then the center of G is non-trivial. Okay, so how do we prove this? Well, it's a corollary, shouldn't take long. We just apply this proposition to the case where G acts on itself by conjugation. So let G be a P group. Acting on itself by conjugation. Okay. Oh, unfortunately, I need to turn the page. So G acts on itself by conjugation. Okay. There we go. Right. Then look at the class equation for G. Since G is a P group, the previous proposition this tells us that the number of elements of G is congruent to the number of elements of the center of G modulo P. Okay. Now, G is a P group. That means that the order of G is P to the N. And P to the N is divisible by P, so P to the N is congruent to 0 mod P. Here, N is bigger than or equal to 1 by the definition of P group. Okay. So this tells us that the order of the center of G is divisible by P. It's congruent to 0 mod P. Okay, but the identity element is at least in the center of G. To see that, you know, it should be clear, but like E times G is G, which is just G times E for all G. So the identity element is always in the center. So the center has at least one element. Now the number of elements of okay, so the number of elements of the center is at least one, and it's a multiple of P. So it can either be like P or 2P, but it can't be exactly one. It has to be strictly greater than one. So this tells us that the center of G has at least P elements, strictly greater than one, and therefore the center is non-trivial. In other words, the center is strictly larger than just the trivial subgroup. Okay, and that is just the information coming from the fact that the G has P to the n elements. Okay. Okay. In general, like there are lots of finite groups with whose center are just trivial. You know. Okay. Okay, so let's take let us take a break until 12:45 and then continue. And we'll start talking about C-lob subgroups. Okay, thank you guys. So see you in like about 7 minutes.